Hello, my name is Jade Knighton, and welcome to my presentation for the Center for Diverse Leadership in Science Summer Series. I will be talking about soil contamination and remediation techniques. So a little bit about me. I completed my bachelor's degree at the University of Texas at Dallas, where a lot of my coursework was focused in hydrogeology. And through that, I was able to go to a hydrogeology field camp at Clemson, and I was also able to get a lot of good field experience at UT Dallas as well. And through that, I did learn valuable skills relating to soils, soil testing, and as well as soil classification and all sorts of things like that. So here's going to be the outline of my talk. I will go over the most commonly used remediation techniques, and included in this, I will talk about bioremedial techniques as well, which use the biosphere and the actual environment to help clear contaminations. And then I'll go into the factors which can affect these remediation efforts and kind of give guidelines to see which technique would be most effective in which situation. And this would include broadly the soil characteristics as well as the characteristics of the contaminant itself. And then I'll wrap up my talk just by talking about some resources on both the local and federal level, which do deal with these industrial contaminations and that pose environmental and public safety threats. So first, we can talk about soil contaminated with organic chemicals. So most commonly with organic chemicals, physical and chemical methods will be implemented. And these are also the earliest methods which were developed for soil remediation. Now these methods might be either in situ or ex situ applications. In situ would be treating the soil in place, whereas ex situ would involve excavating the soil and taking it somewhere else to be treated. And so in ex situ situations, the soil might be incinerated or forcibly leached, which would mean pumping water through the soil to pick up the contamination either in solution or in dissolved load and have the water carry out that contamination. And at that point, the water can be disposed of and the soil is free of that contamination at that point. But ex situ treatments are very expensive because you do need equipment. They are labor intensive as well, and also quite disruptive to the ecosystem. One thing that we may not think of because we can't see it all the time, it's not in macro scale, are that there's a whole ecosystem within the soil. And these are mostly very small organisms such as bacteria, nematodes, but even root systems of plants and ants, insects, things like that. So there's an entire ecosystem that goes on there, and physically removing the soil, of course, can be quite disruptive. It can destroy earthworm burrows, it can destroy root systems. So that is one thing that is to be considered. In situ remediation might include the removal, sequestration, or stabilization of the contaminant. And this can be achieved by flushing, leaching, heating the soil in place, or using vacuum extraction. And these can be carried out in a number of different ways. For example, with the heating, sometimes an actual plastic cover is placed over the soil, which traps heat that comes in. So that is one way that can be done. And the type of treatment depends on the contaminant itself. Like, is it oil soluble or is it water soluble? And also, certain compounds can be applied to immobilize or stabilize the contaminants, which would hold them until the bacteria and the microbial agents which are native to the soil can break them down naturally. And these type of chemicals are called surfactants. So bioremedial techniques can use enhanced plant or microbial action to degrade the contaminants into harmless products. And this is most effective in biologically diverse ecosystems and is also most effective for contaminations of PAHs, PCPs, and TCEs. Bioremediation is typically done in situ, but it can also be done ex situ if needed. And it depends on the native soil organisms, if there are organisms present which can perform this task. So bioaugmentation is a form of bioremediation which involves introducing species selected for their ability to degrade contaminants to augment the natural population. So just to kind of help the breakdown and degradation of a chemical pollution. Biostimulation can also be used, which uses technology to assist the naturally occurring microbial populations to break down chemicals. And this solves issues such as inaccessibility of the contaminant if the contaminant is bound to soil particles, but also issues such as lack of nutrients, which might inhibit microbial growth, electron donor substance availability, or electron acceptor availability as well. So bioremediation may not be possible if the site is too highly contaminated, because that might just be too much for the bacteria to break down. It might be so toxic that it hurts the population. We see reduction in numbers, in which case their effectiveness is reduced. Or if it's co-contaminated with another substance which is toxic to the bacteria and to the soil microorganisms as well. So oil spills are an interesting case of how bioremedial efforts are used and put into action. So many commonly encountered bacterial and fungal species are known to break down hydrocarbons. And I have here two examples of times in which this was used. So in 2012, there was an offshore drilling rig explosion in the Gulf of Mexico, and oil leaked into the ocean and began washing up on the shore. Within weeks, the native bacteria had degraded most of the lighter components of the oil. So what they did is they used dispersant chemicals, which was able to break the oil into smaller droplets, which were more easily degraded by the bacteria. Also in 1989, the Exxon Valdez oil spill, which happened in Alaskan waters, oil was washing up into the pebbly beach, and the cold water was also nutrient poor, and it wasn't really good for supporting large bacterial populations. So bioremedial efforts were used, and the oil was actually fertilized. So the bacteria were allowed to flourish in the oil and help break it down. But since the fertilizer was specially formulated, it was not soluble in water. So this was a really good thinking, because that way any eutrophic effects were avoided. And for those interested, eutrophication is a very serious environmental issue in aquatic environments. It usually involves fertilizers and fertilizer runoff, namely nitrogen and phosphorus. And what happens is these nutrients added into the water can promote bacterial and algal blooms, harmful algal blooms. And these proliferation of bacteria and algae actually end up clouding the top layers of the water. And that can physically block sunlight from reaching aquatic plants. Then, since those aquatic plants can't photosynthesize, they end up dying, which then their decay further spurs bacterial growth. And this is a problem because it's a problem for the food web. The aquatic plants are producers, so any organisms which rely on them for food would also be at risk. They would probably die. So it's bad. It's bad all around. It's bad for biodiversity, and this is a naturally occurring thing in closed systems, just ponds, lakes, things like that. It does happen over time, eventually. But when the nutrient enrichment is anthropogenic in nature, we would like to avoid that if at all possible. And typically it comes from over-fertilization or poor timing of fertilization from fields. But something like this could have caused it as well. But luckily they thought ahead and they wanted to make sure that they weren't going to have any eutrophic effects on the environment. So that was very good thinking on their part. So here in the picture you can see, here in the picture I have in the top right corner, you can see there's a lot of black here on the side, and this was the untreated side, the side which was unfertilized, and the bacteria were, whatever bacteria was there, was just trying to break down on its own. And on the left, you see this other side, which is much, much cleaner. This is where it was fertilized. So you can see that the fertilization really helped the bacterial community and allowed them to break down the oil much more effectively. And here's a graph which also describes that. This is the index of crude oil, which was remaining, and then the time after treatment. And this green band here represents the fertilized areas, and this brown band is the non-fertilized areas. So you can see the slope here is much steeper than the one here, so we're getting faster reduction of crude oil, faster cleanup. So phytoremediation is a bioremedial technique which involves using plants. Phytostabilization is its most basic form, and this would involve growing plant cover in order to stabilize the contaminant and limit its movement. The plants can do this by physically providing a barrier which stops the movement of, which slows water erosion and wind erosion as well. But the roots can also help with leaching below the soil profile, and also absorbing part of the contaminant, so long as that contaminant is not harmful to the plant. It can be quite sustainable. Plant root systems can also excrete substances which can enhance microbial growth and accelerate the contaminant degradation process. And this is referred to as enhanced rhizosphere phytodegradation. Now, the positive aspects to this are that it's particularly helpful if the area which is contaminated is broad in area, with only moderate concentrations of organic pollutants at shallow depths. Now that's important because, of course, the root systems are usually only contained in the O horizon, the very top of the soil profile. So not all plants can reach down to lower horizons to pull out contaminant if that was needed. This also causes little site disturbance and is inexpensive, but it does take a lot of time. So it's not a quick fix by any means. And here in my picture, these are the two types of phytoremediation: hyperaccumulator phytoremediation and enhanced rhizosphere phytoremediation. So here on the hyperaccumulator side, the plant uptakes the the contaminant into its roots and incorporates the contaminant into its structure. And then once the plant either is ending its life cycle or once it's consumed as much as it can, we can cut off this part, we can remove the plant and dispose of it. We would need to do that because if we allow the plant to stay there, to die there, and to become incorporated into the soil, then we're not really removing the contaminant if it's simply been sequestered. So we would have to remove the plant to remove the contaminant. In enhanced rhizosphere phytoremediation here on the right side, the plant actually exudes from its roots a chemical signal to surrounding bacteria, which tells them to, which helps them speed up the degradation of the contaminant. So our next category, we have our inorganic contaminants, and there are three primary methods in order to take care of inorganic soil contamination. So there's elimination or reduction of the amounts of the toxin applied or that is allowed to reach the soil. There's immobilization of the toxin to contain it, or removal of the toxin from the soil by chemical, physical, or biological means. Now, reducing the soil application would involve considering the likelihood of soil contamination and resulting from activities in addition to reductions in continued applications. So this would be a forethought. This would be something that would be classified as prevention of inorganic contamination. In the second, immobilizing the toxins involves inhibiting the plant uptake and leaching by draining water. It breaks the soil plant animal cycle by becoming a sink for the contaminants, and the soil is basically just used as a sink for it. An example of this would be liming the soil in order to reduce the mobility of heavy metals. Bioremedial measures can include utilizing plant species, which we talked about in phytoremediation, which have high propensities for metal uptake in the soil. And we can use indicator plants, which can be used for assessing the level of metals within the soil. Excluder plants can also tolerate high levels of contamination, but they don't uptake the metal itself. And then hyperaccumulator plants are those which can uptake the metal and sequester it and become a sink for the contamination. So the factors which affect the remedial techniques and the effectiveness of the remediation are the soil itself, and I will talk about chemical and physical activity within the soil and where that happens, as well as how the soil structure and composition can affect the chemistry of the soil. And then I'll talk about contaminants and the different type of contaminants and how they behave within soils. So the majority of the chemical and physical activities within soil takes place in the colloidal fraction. And the colloidal fraction is the part of the soil. It's categorized as under both the mineral portions and the organic portions of the soil. But of the mineral portion, we have all sorts of sizes in the mineral portion of the soils. We have pebbles all the way up to cobble sizes, and then all the way down to clay sizes. And so when we're thinking about the colloidal fraction, we first start with the fine earth fraction of the mineral fraction of the soil. The fine earth fraction are those that are sand-sized grains, silt-sized particles, and clay-sized particles. And the clay-sized particles are the very smallest. And they are part of the colloidal fraction. Whereas from the organic side of soil content, humus particles, which are again very, very small microscopic particles, are the other part of the colloidal fraction. So the colloidal fraction includes the very smallest particles within the mineral portion and the soil organic matter portion of the soil. So colloids affect the chemistry and physics of the soil in a way that affects the very nature of the soil, and it affects stability, its ability to be restored, the soil's productivity, its ability to be contaminated, and also the movement of fluids through the soil. Now, colloids are typically made of clay and humus particles. And as I mentioned, they're the smallest solid constituents of the soils. They're highly reactive and they have electrically charged surfaces. The overall charge of the colloidal fraction is negative, and that is due to the structure of clay particles. And depending on the type of clay, some of them might have one side which is positive, but mostly we consider the colloidal fraction to have a negative charge. So most of the interactions which take place will be with cations. The size and shape of colloids also gives them large surface areas to work with. When you think of a clay particle, you know that they're more flat and platy, as opposed to a sand grain, for instance, which is a little more spheroidal. And the charged nature of colloids allows the particles to hold together tightly enough to reduce water movement and fluid movement through the soil profile, but it is loose enough that plants can still access nutrients. Now, colloids can also combine with a number of substances, and this includes water molecules, biomolecules, viruses, toxic metals, and pesticides. So the character of the colloidal fraction within the soil that you're looking at, the type of clays there, the amounts of colloids which are present within a soil can affect the degree to which the contaminant can hang out in the soil, and also if it can bind to the soil itself, and it'll become much more hard to remediate that way. So the soil structure is also important when we're talking about soil chemistry. And the soil structure describes the spatial arrangement of particles to form aggregations, pores, and channels within the soil. And decrease in particle size increases the specific surface area. So smaller particles and higher percentage of smaller particles can actually affect what's happening on the surface of those particles. So soil texture can influence the fundamental surface phenomena which occurs on the surface of the particles. So both gases and dissolved chemicals are attracted to and absorbed by mineral particle surfaces. Weathering also takes place on the surface of mineral particles, which can release elements into the soil solution. The soil solution is the fluid within the soils. It's mostly water, but also anything that has been picked up and been carried in dissolved load. So the soil solution often contains both water and anions as well. Soil texture can also influence the charged particle surfaces and the water films between them, so how they're attracted to each other and how they form aggregates within the soil. And also microorganisms tend to live on the mineral surfaces as well, the particle surfaces, which, as we talked about, microorganisms can be very important in soil remediation. So a little bit more about the soil composition. This would be clay content, because we talked about how colloidal particles are where a lot of the chemistry is happening with the soils. So clay particles, they have large specific areas, and this results in a really tremendous capacity to absorb water and other substances. And the type of clay minerals is also important because that affects the water holding capacity and the chemical absorption of the soil, which are of particular interest when we're talking about contamination and how that contamination is interacting with the soil. So the clay-dominated layers might have very small, convoluted pores, which slow the movement of air and water. And this can result in more fluid holding capacity, but reduced fluid movement. And also the soil organic matter composition and how much of that is within the soil is of interest. And this would be defined, the soil organic matter is defined by its carbon content, and it affects physical, chemical, and biological properties, as well as ecosystem functions, including bioremediation. So the soil organic matter also provides most of the soil's cation exchange capacity and water holding capacity, and it also supplies the humus, which is part of our colloidal fraction. So here in this picture, I have this is a SEM picture of clay particles. So you can see they're very flat and plate-like, and some of them are stacked up on top of each other. So this is what we're talking about when I'm talking about where these chemical interactions are taking place. So now we can go back to talking about how organic chemicals interact with the soil. So once in the soil, organic contaminants can follow a number of different paths, and this includes they may volatilize and turn into gas and escape to the atmosphere. They may sorb to colloid surfaces. They may leach out into the groundwater and move away from the area. They may undergo chemical reactions. They may be decomposed by bacteria. They may be picked up in solution and by overland flow and run off to a local base level, or they may be consumed by plants and animals. Trifluorine, PCB, gasoline, and diesel are mainly lost via volatilization, and the absorption ability of a contaminant is determined by both the chemical itself and the soil. And we talked about a couple of reasons for that when we talked about soil characteristics. Diquat and paraquat are prone to adsorption by silicate clays, for example. So in a soil of high silica clay content, we would be concerned, just as an example, if it was contaminated with a substance like diquat or paraquat. So leaching tendency is also dependent on the contaminant's solubility in water and its potential for adsorption. So things like chloroform, phenoxyacetic acid, are highly soluble in water. And chemicals prone to adsorption will not be as prone to leaching. So chemicals which readily bind to colloidal particles will be less likely to join the groundwater system, contaminate it, and spread it out that way. They'll be more likely to post up in the soil, and so the soil itself is what would need to be monitored. So in general, herbicides are also more mobile in water, so herbicides might be a concern with leaching and groundwater contamination. So groundwater contamination by pesticides can occur even from normal agricultural use, and this can also be of long-term health concerns. So some pesticides can overgrow chemical modification independent of soil organisms. They may interact with sunlight, and chemicals which are known to interact with sunlight are things like DDT, diquat and triazines, or they may undergo hydrolysis and interact with the soil water, such as malathion. Now, other pesticides can undergo chemical modification through interaction with the soil biosphere. And as we talked about earlier, some soil organisms such as bacteria, fungi, and plants are effective at actually removing contaminants such as pesticides. So plants can assist in the breakdown and degradation of pesticides. We talked about ways that they might do that. They might exude enzymes from their root system, which will catalyze the breakdown of compounds. And plants can also take up pesticides and store them in their actual structure, where they can then be more easily removed. So pesticides vary in their residence times within soils, and some might only last for a few days, such as organophosphates, whereas others may have residence times in decadal, on the decadal time scale, such as PCBs and DDT. Now, continued use of the same pesticide can also increase the rate of microbial breakdown. The microbes can sort of microevolve in order to prefer these contaminants as a food source, in which case they will become more effective at breaking it down, and more exposure might lead to breaking it down more quickly. So common organic pollutants include plastics, plasticizers, lubricants, fuels, solvents, pesticides, things like that are all synthetic organic materials which are manufactured every year. And these can be extremely toxic to humans and other parts of the ecosystem. And they can be introduced into the environment through accidental leakages, spills, burial, or by planned spraying and application treatments, which affect places where they're not supposed to affect. So industrial pollutants, including petroleum products such as benzene and complex polycyclic aromatic hydrocarbons, and also manufacturing solvents such as trichloroethylene or explosives such as TNT. They can also affect the ecosystem. So for example, PCBs can disrupt reproduction in birds and cause cancer. They're also known to cause hormonal imbalances in humans and other animals. And most intensely contaminated sites are typically in close proximity to manufacturing plants or storage facilities. Inorganic substances, which are common contaminants, include mercury, cadmium, lead, arsenic, nickel, copper, zinc, chromium, molybdenum, manganese, selenium, fluorine, and bromine. That's boron. So varying degrees of toxicity exist within each of these heavy metals. Cadmium and arsenic are extremely poisonous, while boron and copper, manganese, and zinc are relatively minimally toxic to animals. And in fact, manganese and zinc in certain species are necessary nutrients. Well, yes, they are necessary nutrients for certain plant and animal species. Copper as well, actually. So sources include fossil fuel combustion, metal ore smelting, manufacturing processes, which can release these elements into the atmosphere. And once in the atmosphere, they can settle out, and they can settle out onto the soil and contaminate the soil that way. So inorganic toxins do not decompose or degrade naturally, rather they accumulate. And for this reason, some contamination sites are historical. So they're not something that has happened recently, but rather they have been that way for a long time. But since they don't break down, they're still there. So inorganic contaminants that are introduced can be introduced into living tissues through both respiration and ingestion. And these heavy metals can accumulate through the trophic levels. They accumulate in plant and animal tissues, with higher concentrations being found in organisms which are higher up the food chain. Because the higher up in the food chain, the more organisms below it have consumed it and been contaminated by the particular heavy metal. And so once it finally gets to members at the top trophic levels, then they're consuming quite a bit of accumulated metal at that point. So common inorganic pollutants, a little bit more about them and how they occur. Chromium is necessary in small amounts, but is carcinogenic in large doses. And it's typically introduced into the environment in steels, alloys, and paint pigments. Now, it can be immobilized or stabilized by chemical reduction to trivalent chromium. So boron contaminates soils through irrigation, water, or excessive fertilizer application. It is easily absorbed by colloidal particles, but can still be taken up by plants as well. Boron contamination is also typically a localized problem. So fluorine toxicity is generally localized as well, and it's introduced by animal drinking water or as fumes from industrial processes. Fluorine is ingested by animals or absorbed into the soil, and it's highly insoluble within the soils. So selenium is mainly introduced by mineral weathering, and it can accumulate in soils and plants to toxic levels, and really it's most commonly a problem for more arid regions. So once we've identified a place that requires remediation, there are a number of avenues which we can go through at both the municipal level, the local level, and at the federal level. And there are agencies which are able to help and help lead remediation efforts. And so locally, here in Los Angeles, the County Department of Public Health is the one which oversees remediation efforts. So the website I put there, and when you go to that website, it takes you through different menus where you can select what type of problem it is, if it's industrial, if it's residential, and also and it provides, based on what you pick, various resources of agencies to call. Sometimes the county department takes care of it itself. Sometimes it has a third-party provider who's able to help. But anyways, you can go to that website and you can click through and find resources specific to the site that you're looking at, the location. And in some cases, there are things in process in that site, and they do post what they're doing to help that particular contaminated area. So federal resources are of course, carried out by the EPA. The most important of these, and the most, I guess, well known of these, is the Comprehensive Environmental Response Compensation and Liability Act, or CERCLA. It is a trust fund which was created in response to environmental and public health hazards which were posed by the chemical and petroleum industries. And it provides a method of holding persons accountable for releases of hazardous waste at abandoned or closed sites, as well as a means to take care of sites for which no responsible person could be located. And this response is managed by the EPA, the Environmental Protection Agency. And each site is a very complex, multi-phase cleanup process, but they all begin with a preliminary assessment. And the site is characterized, The hazard level is assessed and remedies are then proposed. And eventually remedial action can be taken as well. Now this can be a very slow process. This can be decades in the making from the time that a site is identified, put on the Superfund list, and then taken off of the Superfund list. So this, of course, is something which might not be an immediate fix, but as we've talked this entire time, rarely are these contaminations taken care of very quickly. So, yeah, if you have any more, if you have any questions or you want to look further into CERCLA or the EPA, I have included links here at the end of my talk. So here is a link to the Superfund cleanup process and to the CERCLA overview, as well as to the Los Angeles County Department of Public Health. So thank you so much for listening to me, and let me know if you have any comments, questions, or feedback, and have a great day.